symmetry. So what kind of objects have cylindrical symmetry? Anything where the electric field is emanating out cylindrically. So rods, cylinders. The rod is just basically the name for a very thin cylinder, you know. But the rod is actually a cylinder too. So rod is like this, you know. Or you can say a line charge. Sometimes they're called line charges. Line charge is even thinner than a rod. The rod might have some dimension like this, whereas a line charge is usually thought of like that. You see, so this would be rod, this is line charges, and a cylinder is usually thought of with a bigger radius. Okay, so what their electrical fields look like? They emanate out cylindrically. You see, like that. Same thing with this. Kind of makes it like a circle. And then same thing here. And then on the other side, it's hard to draw. You see. But that cylindrical nature doesn't last that long. After a while, it begins to diverge, right? And when you go far away, they also should look like a point charge. In other words, nature's default symmetry is spherical. Point charges and spheres have spherical symmetry. So that's the nature's default symmetry. So the electrical field of a cylinder stays cylindrical for a little bit. And then after that, it starts to turn into spherical. So what we can do again is we can take the equation that we have when we were doing the chapter, the earlier chapter, the equation that we derived for the general electrical field of a rod in the middle. I think anyone remember that? General electrical field for a rod in the middle. Wasn't it something like this? K, Q, D over X squared plus D squared to the, should it be 3/2 or 1/2? I remember something like that. Or maybe it was X squared plus, L squared plus D squared over 4. I think it was something like that. L squared over 4 plus D squared to the 1/2 or 3/2. Now, how can I know if it's 3/2 or 1/2? Well, I think it was 3/2. Yeah, I think it was 3/2. But I could do my test now to see what should this equation give me when I go to infinity. You see, so this is the electrical field of the rod in the middle. So when I take the limit as d goes to infinity, what should happen? So when d goes to infinity, this one dies out. And then this one becomes what? K q d over d squared to the 3/2, so it becomes d cubed. K q over, there you have it, d squared. Aha, so that works. You see, the line charge begins looking like a point charge. You see, so so that means this was 3/2. You see, so we could plot this to find out I'm just going to plot it without the KQ, just with some number for the length. So let's see, what would that look like? Y equals, let's say the x divided by, what is it? X to the power 2 plus, let's say the length of the rod is 2 meters. We'll make it easy. The length of the rod is 2 meters. Oh, then it'll just be 2 squared over 4. Oh, then it'll just be 1. Oh, that makes it identical to the electric field of a plate. Yeah? Oh, no, not the plate. It makes it identical to the behavior of the electrical field of a ring. So this is the middle of the rod, and this is the ring. Oh, that's interesting. They behave exactly like each other, except here you're putting the radius of the rod. I mean, the radius of this is the ring, right? So yeah, here you're putting the radius of the ring, and then here you're putting L squared over 4, the length squared over 4. Yeah. So if it's a 2 meter length ring, 2 meter length, a 2 meter length rod, it has the exact same behavior as the ring. Oh, so this is kind of tied to the lab that you're doing for Tuesday, right? You're trying to prove that the electrical field increases linearly for the rod. Oh, hold on. No, that doesn't make sense. Hold on. What did I tell you guys for the lab, the one that on Tuesday? I think I said the rod should decrease linearly, right? Decrease linearly, then decrease as a square function, right? Something doesn't make sense about my equation, because that would make the electrical field of a rod increase linearly, just like for the ring. I don't think it should behave like that. Is something wrong with my equation? Anyone have that? Daniel, do you have that? What is the general equation for the electrical field of a ring in the middle? We derived that, I think, Monday or something.
Oh, yeah, let me check right now.
I think my equation is wrong.
For a uniform rod, right?
Yeah, uniform rod in the middle.
So it was a 2KQ over.
Oh, okay. 2KQ, there's nothing on the top, like a D or anything?
No.
Oh, I see, I am wrong. I figured it out.
There's a D at the bottom, and then the square root of L squared plus 4D squared. Yeah. Like
oh, L, so 2KQ over D square root of? Oh, it's a square root function.
Yeah, square root function.
Oh, and then what is it? L squared over 4 plus D?
No, it was
L squared plus 4D squared.
Yeah.
Oh, I see. Very different. You see, this test led me to think that I was right. So this is actually a good thing that happens, you know. It shows you that you can't just rely on one test to say, oh, okay, my equation is right. My equation was working, but then when I graphed it, I said, wait a minute, it can't be that as I go away from the rod, that the electrical field should increase. That didn't make sense to me. It should decrease linearly, not increase linearly. But the ring is different. The ring should increase linearly because the field lines come down. Here, the field lines do what? See, they don't do this. They don't do this for a rod. You see that? That's how you make sense of all this. The rod doesn't do this. It just goes out straight, then curves. So that means it should decrease linearly, whereas the ring, it increases linearly, then starts to reach its max, then it starts to decrease, you see. So, okay, so it's a very different looking function. But now let's do our test. Limit as d goes to infinity, what happens? 2kq. So when d goes to infinity, the L disappears. L disappears, so then you have square root of 4d squared, right? Only that one survives. And then what happens there? Square root of 4d squared is 2d. Okay, there you go. kq over d squared. Yep. Nice. Okay, so now the test works. So now if we graph that, let's see, I'm curious to see if the electrical field of a rod will look kind of like the plate. It seems like it kind of looks like the plate more, but not quite. So it goes 1 over the, oh, this is 1 over, and then it's the x is on the bottom, right? And then it's what? If, let's say the length of the rod is 2 meters, so then that will make this number a 1, but then it's a square root function here, right? Okay, there you go. Oh, very different looking. Okay, so the red one is a plate, this one is a ring, and the rod is like this. So it depends on the radius of the rod where I start on this. So it's a 1 over x function, right? So that's kind of connected to your lab on Tuesday. Remember, you're supposed to show that it's a 1 over x function, right? And then, okay, so it starts out somewhere here, depending on what the radius of the rod is. Then it starts to decrease 1 over x. So it's a very different function. This one decreases linearly, right, as a linear function. This one increases linearly, then drops. But eventually, when you go to infinity, they should all go as 1 over x squared. Even this one first goes as 1 over x. So how would you know that it's going as 1 over x? Again, you just double the distance. So let's say the distance here is 0.242, right? And the electric field is 4. If I double the distance, what would that be? 0.48, right? 0.48. What should the electrical field be? Yeah, it should be half of the electrical field at 0.24. You see, it's a linear function. 0.48 is 1.8, and then 0.24 is 4. Yeah, it's about half. You see, but then when you go to large distances, you go to 4, it's 0.06. If I go to 8, it should be 0.015. So is that 1/4? Let's see here. 0.06. What's 1/4 of 0.06? 0.06 divided by 4. 0.015. Yeah, there you go. You see? So already over here, it's turned into a 1 over x squared function. You see? So for a 4 meter rod, by a distance of 4 meters, it's already behaving as 1 over x squared. You see that? For a 4 meter rod. So that means as if you, that one would work for fluorescent light bulbs. If you're the same distance, if whatever the length of the fluorescent light bulb, if you are the same distance away from that light bulb, the intensity of the light bulb already decays as 1 over the distance squared of the light bulb. But when you're close to it, it behaves as 1 over the distance. You see? Okay, so then how would I do the close approach here? Limit as d goes to 0. So then I would say, if I'm close, then this disappears. And then only this is left, square root of L squared. Right? Because this is gone. And then we're left with what here? 2kq over dl. Okay, keep this in mind because we're going to derive this equation using Gauss's law. We're going to derive the equation for the electrical field near a cylinder or near a line. And the answer we get should be identical to this guy. Okay, so now let's derive the equation for the line charge or rod or cylinder. So I'm going to take a cylindrical Gaussian surface to exploit the cylindrical symmetry. Then I'm going to say, okay, the electrical field comes out this way, but it doesn't, since it doesn't bend yet, it doesn't come out from these two ends, from the left end, from the right end. It only comes out through the surface of the cylinder, you see. So then the flux is equal to EA times Q enclosed over E0. E is the electrical field that we're trying to find, times the surface area. So what's the surface area of a cylinder? So depending on what that distance is, R, the surface area of a cylinder is going to be 2 pi r times the length of that Gaussian cylinder. All right, so 2 pi r gives you the cylinder, the circumference of that Gaussian cylinder. 2 pi r gives you the circumference of that Gaussian cylinder, and then L gives you the length times Q enclosed over E0. Okay, so then E times 2 pi r L. So now divide this by this. So what is L? L is the length of my Gaussian cylinder. Q enclosed is the charge. See, the rod could be this long, but Q enclosed is the charge enclosed within the dimensions of the cylinder. You see, Q enclosed that divided by that. Well, that gives you the linear charge density of the rod along the rod. So it gives you lambda over 2 pi r E0. You see, because Q over L is the linear charge density of the rod. So it just tells you how much charge is included in the cylinder or the rod per every unit length of the rod. You see, lambda, and then divided by 2 pi r E0. So notice the behavior of the electrical field, 1 over r. That's what we just showed it here, 1 over r. You see, by doubling the distance, I'm halving. I'm going from 0.24 to 0.48. I'm halving the electrical field. So when I'm close to the rod, it's a 1 over x behavior. You see? Now, this equation should be the same equation that we just derived by taking the limit of this, you know, as when d goes to 0. So 2k q over dl, let's write that here. 2k q over dl. That should be the equation that we just derived. It looks very different, but it should be the same. Q over L is what? The linear charge density of the rod. D is the same thing as what I'm calling R here, because D is the distance from the rod. So we can just replace that by R. So then what's K? K is written as 1 over 4 pi E 0. Uh-oh, there you have it. Lambda over 2 pi E 0 R. There you have it, identical, exactly identical. So using the general equation for the electrical field of a rod, we get the same answer as the Gauss's law way by exploiting the cylindrical symmetry. Okay. So there's two general formats that we can write down the electrical field of a rod. So remember that this only works when you're close to the rod, right? When you go far away, then it starts dropping as 1 over distance squared, right? So there's two general ways we can write this way or this way. I sometimes like this way because it reminds me of the kq over r squared. So kq over r squared is the electrical field of a point charge. 2k lambda over r is the electrical field of a cylinder. So it kind of looks like that, except you've got 2. Instead of q, it's q over l. Q over L. So in terms of units, it's the same because this is Q over L. So it's got units of charge. See, units of charge, units of length times units of length. You see, so the point charge's electrical field is length squared, whereas here you've got charge per unit length. So it's got coulombs per meter. So it has to be the same units because we're still talking about electrical field, you see. So it just looks very different like this. It looks like it's only got 1 meter, but actually this has a coulombs per meter in there, you see. Okay, how about spheres?